students. Now we come to the next part of this arithmetic function, which is called the Moebius, M-O-E-B-I-U, that's Moebius inversion formula or Moebius function. So by Moebius function, how we define it, the Moebius function denoted by mu n, Moebius definition. The Moebius function, the MF means Moebius function, mu n is defined by this one. Mu n will be equal to 0 if n is equal to 1, which means mu of 1 is equal to 0 if n is equal to 1, and it will be equal to 0 if there is a square which divides n for some a greater than 0. Sorry, this is mu of n is equal to 1 if n is equal to 1, and it will be equal to 0 if there exists a square which divides n, and it will be equal to minus 1 to the power r if n is a product of r distinct primes p1, p2, dash dash pr, where pi's are distinct primes. So this is a definition of Moebius function, which states that mu n is equal to 1 if n is equal to 1, and it will be equal to 0 if a square, if there exists a square which divides this n for some a greater than 0, and it will be equal to minus 1 to the power r if n is a product of r distinct primes, where pi's are all distinct primes. I varies from 1 to r. For example, we have here, what is mu of 1? Because when n is equal to 1, we have mu of 1 is equal to 1. What is mu of 2? It is equal to minus 1, because 2 here is a prime number, so n can be expressed as a product of 1 into 2, so it will be minus 1. There is only one prime here, so minus 1 to the power 1, which is equal to minus 1. Mu of 3 also the same, will be equal to minus 1. You have to use this definition, third definition, that is to the power 1, which is equal to minus 1. What about mu of 4? Mu of 4 here is equal to 0, because there exists a square, that is 2 square, since 2 square divides 4. So it satisfies the second definition. Since 2 square divides 4, therefore mu of 4 will be 0. And mu of 6 here, which is called, what is 6? 6 can be written as 2 into 3, that is a product of 2 distinct primes. So by this third definition, it will be minus 1 to the power 2, since it is a product of 2 distinct primes, which is equal to 1, and so on. As you can write here, 6 is equal to 2 into 3. Now let us come to this theorem, which is an important theorem on Moebius function. The function mu n is multiplicative and summation of mu of d, where d runs over the divisor of n, is either 1 if n is equal to 1 and 0 if n is greater than 1. We need to prove this result. First of all, we have to prove that the function mu n is a multiplicative function. By multiplicative function, we means that mu of mn is equal to mu of m into mu of n whenever GCD of mn is equal to 1. And the second part of this theorem is that you have to show that summation of mu d is either equal to 1 if n is equal to 1, or it is equal to 0 for n greater than 1. So first of all, let us show that mu n is multiplicative. So if let GCD of mn is equal to 1. So if either m is equal to 1 or n is equal to 1, then mu of m will be equal to 1 according to the definition here. It is equal to 1 if n is equal to 1. So mu of m is equal to 1, or mu of n will be equal to 1. So therefore mu of mn will be the same as mu of m into mu of n. With one of them equal to 1, then mu is a multiplicative function. Now if m is a product of r distinct prime p1, p2, dash dash pr, and n is a product of s distinct primes q1, q2, dash dash qs, then what is mu of m? How many distinct primes are there? There are r, and according to definition, we should use this third definition of Moebius function, that is minus 1 to the power r, and here there are s distinct primes, so mu of n here will be minus 1 to the power s. So therefore mu of mn, which is equal to a product of r plus s distinct primes. It will be minus 1 to the power r plus s, which is same as mu of m, that is minus 1 to the power r into minus mu of n. So therefore mu is a multiplicative function if n is of this form. N is a product of r distinct primes and q is a product of r distinct prime. Next case is if m is equal to product of r distinct prime powers, say p1 to the power alpha 1, that is of this form, p2 to the power alpha 2 dash dash pr to the power alpha r, and n is equal to q1 to the power beta 1, q2 to the power beta 2 dash dash qs to the power beta s, with at least one of these, at least one alpha I is greater than equal 0, or beta I is greater than greater than or equal to 2, or beta I is greater than equal to 2. So it means that if one of this is a square, means either alpha 1 is equal to 2 or alpha 2, at least one of them is a square, so means there exists a square which divides m. And by the definition of Moebius function, that is if mu n will be 0 if there exists a square which divides n. So here in this case mu of m will be equal 0, or mu of n also will be equal to 0. So if n is a product of r distinct prime powers, n is a product of s distinct prime powers, then we have mu of m here will be equal 0, or mu of n will be equal 0. So therefore mu of mn will be equal to 0, because there exists a square which divides this product, and which is same as mu of m into mu of n, because mn here is nothing but p1 to the power alpha 1, p2 to the power alpha 2 dash dash pr to the power alpha r, and n is a product q1 to the power beta 1 dash dash qs to the power beta s, with at least one of these alpha i's is greater than equal to 2 or beta I is greater than equal to 2. It means that there exists a square which divides this. So therefore mu of mn will be equal to 0, which is same as mu of m into mu of n equal to mu into mu of n. So this implies that mu here, mu n, is a multiplicative function. Next part, we have to show that summation of mu of d is either equal to 1 or 0 if n is equal to 1 or if n is greater than 1. And for that, let us take if capital Fn, because mu is a multiplicative, if capital F of n is called summation of mu of d, we have to show that summation where d runs over the divisor of n. So if capital Fn, we denote this notation summation of mu d where d runs over the divisor of n, then by one of the theorem of multiplicative function, if Fn is multiplicative, then capital Fn is called summation of f of d where d runs over the divisor of n. This is an important theorem I've already explained to you. This is again multiplicative. So using this theorem, I'm applying here, instead of fd, I have shown you we have mu d and mu n, and fn here you compare fn with mu n, which is multiplicative. So by this theorem, it implies that if fn is equal to this, then fn is multiplicative. And since f of 1 is equal to summation of mu of 1, which is equal where d runs over the divisor of 1, so the only divisor of 1 is 1 itself, which is equal to mu of 1, this will be equal to 1 according to definition. So we have f of 1, that is summation of mu of 1, mu of d is equal to 1 if n is equal to 1. So the first part of this is proof. Now if n is a product of r distinct prime power, p1 to the power alpha 1, p2 to the power alpha 2 dash dash pr to the power alpha r, then what is capital Fn? Then capital Fn is equal to f of p1 to the power alpha 1 dash dash pr to the power alpha r, and since f is a multiplicative function, so this can be expressed as f of p1 to the power alpha 1 dash dash into f of pr to the power alpha r. And what is this f of p1 to the power alpha 1? What are the divisors of p1 to the power alpha 1? They are 1, p1 square dash dash p1 to the power alpha 1. So therefore we have f of p1 to the power alpha 1, which is defined as a summation of mu of d, where d runs over the divisor of n. It is nothing but mu of 1 plus. So in general we have here, this can be written, so this implies that, okay, this implies that f of pi to the power alpha I is equal to mu of 1, because the divisors of pi to the power alpha I are p1 pi square dash pi to the power alpha I. So it will be mu of 1 plus mu of pi plus dash mu of pi to the power alpha I. So next after this will be mu of pi square and so on. So as we know that mu of 1 is equal to 1, so we'll replace it by 1, and mu of p1, because n here is equal to 1, so by this definition of this Moebius function, mu of minus 1 to the power 1 only, so it will be minus 1, so be minus 1 because the product of one distinct prime only. But here pi square, there exists a prime, there exists a square which divides this pi square, so it will be equal 0. So from mu of pi square onwards, it will be 0. The sum will be 0, so therefore 1 minus 1 here will give you 0. So therefore f of n, which is defined as summation of mu of d, where d runs over the divisor of n, will be equal 0 if n is greater than 1. So this complete the proof.